Good morning. So today I wanted to talk about the design of everyday functions, which is a bit of a weird title, but is inspired by this really nice book by Don Norman. How many of you have heard of this book or read this book? Okay, if you've never read this book, I highly recommend it. And we'll kind of see a little bit why what on earth this weird-looking teapot has to do with data science and R. In coming up with this talk, kind of lately I've been thinking a little bit about some of the differences within the data science field. Data science is a pretty broad field, and there's a lot of kind of different people doing slightly different things. And one continuum I want to talk about today is this kind of continuum between like the practitioner versus the programmer. So I think the difference here is like if you're a practitioner, you're like doing data science directly, right? The data is right there in front of you and you are interacting with it, you're exploring it. And if anything goes wrong, you can like easily spot the problem and then fix it quickly because the data is right there in front of you. At the other end of the spectrum, I think there's more of a kind of a programmer mindset, where you're no longer directly interacting with the data, but you're interacting with it via some kind of intermediary. So you might be someone like me who like writes packages. Like I don't really do much data science anymore. I just make tools that other people use to do data science. Or you might be putting your data analysis code, data science code into production, where no longer the code is not like running right there in front of you on your computer, it's running in some kind of other computer that's a little bit harder to access. And I think this kind of makes quite a big difference to the way that you write code, because this is all about what happens when something goes wrong. So when you are interacting with code that's right there in front of you, you can hear when your code screams. But when you're either writing an R package or you're putting your R code in production, like no longer is your code screaming directly to you, it's going to break and somebody else is going to scream at you. And so like this is what happens like when I make a mistake in a package, right? Nothing happens to me, like I don't have any problems, but other people have problems and then they complain to me, which we'll see a few of those shortly. And so recently Yihui Xie, the author of Nita, wrote this really nice blog post kind of contrasting another aspect of this sort of tension between the practitioner and the programmer when it comes to like how do you interact with your data science code. So he's written this really nice, it's pretty long, but I highly recommend it, this blog post called The First Notebook War, which kind of discusses some of the tensions between like a notebook-like interface, like which you normally is sort of the primary interface in the Python community with like Jupyter notebooks, and the sort of more like IDE interface that you might find more in the R community. So really, really great. And I think it's important, like as the field of data science gets bigger, to recognize that like no matter where you are on the spectrum, like you can still be a data scientist. And so I don't like, I sit in probably quite a different place to you in this spectrum, but this doesn't make me like better than you, it just makes me different. And I think throughout your career, so I'm kind of put myself like way over here, right? I don't really do any data science, I just make tools for other people. And I suspect most of you are more on this spectrum. You're doing lots of data science yourself, maybe over time, you're building more tools for other people in your team to use, or you're putting more code into production where you're not interacting quite so directly with this data anymore. And so I don't think this is not an inevitable transition throughout your career. You'll kind of move back and forth. But I think it's really useful, and what I want to focus on today is moving a little bit more in this direction. In particular, I want to talk a little bit about some of the differences in kind of coding style between being a practitioner and being a programmer. Because when you're a practitioner, I think you're really having like a conversation with your code and your data. And you can tolerate a lot of ambiguity, like if something goes wrong, it's okay. It's okay for functions to try and guess what you want, because if they guess wrong, you're right there to have that conversation and resolve any problems. But when you're a programmer, you really want your code to complain early and often. So what I want to talk about today is how do you like pick functions that do that? Like why should you do that? And how do you kind of write your own functions to that work in that way? And I'm going to start off with a slightly weird question. And that is like, what makes a good door?
There's this door on the 10th floor of the Vox Media office that I hate so much.
God damn it.
You ever get this door wrong?
Pretty regularly.
Have you seen people misuse it?
All the time, every day. Constantly. I hate this door.
Me too, Kelsey. But here's the thing. As soon as you start looking for confusing doors, they are everywhere.
It's push.
Why?
And I really appreciate that this hotel also has these doors which have pull handles on them and a sign that say push. And so I really like this quote from Don Norman, which is like, when you like use a door incorrectly, it's very easy to think, oh, I'm so stupid, like how could I do that wrong? But when you see many people like again and again and again using the door in the wrong way, it implies it's not a problem with the people, it's a problem with the door. And I think this applies equally to R functions. So when you see R functions that people just like cannot use, like they cannot remember the difference between spread and gather, and they have to Google it every single time, or have to look up the documentation again and again and again, like you shouldn't blame yourself when you're using those functions. You should blame the author of those functions. And so similarly, so people have been asking this since like 2015. So when I look at this and I think, well, maybe there's something not quite right with the design of the spread and gather functions. Another frequent source of complaint is, how do you get rid of a legend in ggplot2? So again, I've just given you a small selection of the many, many, many tweets. And so what I want you to think about is, when you find a function hard to use, you shouldn't necessarily blame yourself. Like, don't think, oh, I'm stupid. Think, oh, Hadley's stupid because he designed this function wrong. And I've kind of included this quote here. This is really aimed at me, not at you. Whenever you think that something is clever and sophisticated, it's very often self-indulgent. So I think it's really important to think about like the design of functions. What makes things in the world easy to use? Like, one thing that makes things easy to use is like these affordances. Like, when you look at a door, can you tell whether to push it or pull it? And so I wanted to talk first with functions about some clear examples of like what makes a bad function, or what makes a bad function. How many of you are familiar with the word what? Okay, this is not like a common English word. This is a specific programming word. And if you've never heard of it before and you want to hear a funny programming talk, I highly recommend listening to this talk. And I will not explain what WAT is, but I'm going to show it to you so that you will understand. So I'm going to show you a little snippet of R code. This is a really simple snippet, right? Hopefully you've probably all used each of these functions individually. You might have created factors before, and you might have tried to combine them together. So what is going to happen when I run this line of code? What am I going to get? So try running this line of code in your head, and if you do so, you'll get 1, 1. What? This is pretty surprising, right? If you concatenate a factor A and a factor B together, you're going to get 2 1s. Or say I have a date, today's date, and I have the time, lunchtime, and I combine those together in a vector. What am I going to get? What? So I get today, and then I get this date. It's even hard to parse this as a date. This is the date in the year 4,210,927 on January 24th. It's pretty surprising, right? This is a what moment. What happens if you do them in the opposite order? If you put the lunch and then today? Well, you get today's date at lunchtime, and you get a date in 1969. What? What happens even if you look at a date time the wrong way? So here I've carefully created lunchtime. I realize probably 12 o'clock is not lunchtime, it might be 1 p.m. here. but I've carefully created in the Belgrade time zone. What happens if I just concatenate that vector with nothing? Well, I lose the time zone. And what happens if I concatenate it with nothing? Well, null? Well, I lose everything and I just get this number. So these functions are surprising, right? These are what moments. Like, it's more surprising than like what. It's like, what? And so I wanted to use this as to kind of illustrate like one aspect, I think, of what makes a good function. And that is like, can you kind of, without knowing the full context of the function, can you just by reading the source code, reading the code of that function, guess what type of thing it's going to return? So I'm going to use type here as kind of a pretty like general. I'm going to use it in the sort of the ordinary language meaning, like the ordinary human language meaning, like what's the type of this thing, not in any kind of specific meaning, but like is it an integer, or is it a factor, or is it a data frame? Like what type of thing do I get when I call this function? And to make it kind of clear that I'm writing this sort of like pseudo R code, I'm going to put the types in these angle brackets. So I can kind of summarize those surprising results that we just saw by saying if you concatenate a factor with another factor, you're going to get an integer, which is surprising. Or if you concatenate just a time zone by a date time by itself, you lose the time zone of that date time. Or if you combine a null and a date time, you get a double. Right? These are all things that are a little bit surprising, and I think by and large it's bad for a function to be surprising. Right? You don't want to be surprised when you're calling a function, particularly a function that is so kind of low level as the C or combined function. And so to think about this a little bit more, we need a little bit more terminology. And so you may or may not know, but in R, there are 4 atomic vectors. So 4 types of atomic vectors. So these are called like atomic vectors because these are kind of the atoms of R. Like pretty much everything more complicated in R is built up, every more complicated data set particularly, is built up from these simple foundations. So we've got logicals, that's true, false, and missing. We've got integers and doubles, which are often collectively called numeric vectors, because in R, typically the difference between an integer and a double isn't that important. And then we've got character vectors. These are the 4 types of atomic vector in R, the 4 building blocks that the vast majority of more complicated things are built up from. And when you're using C with atomic vectors, the rules turn out to be quite simple. Now, so if you combine a logical and a logical together, you get a logical. If you combine a logical and integer together, you get an integer. And if you kind of carefully read this through and you kind of think of this about this a little bit, you might realize, oh, it's easy to represent this in a table. So on the left-hand side, so basically if you combine a logical and a logical, you get a logical. If you combine a double and a double and a character, say, you get a character, right? So this is just summarizing those results. And if you stare at this table for a while, you'll notice that it's symmetrical. Hopefully it's symmetrical. If it's not symmetrical, it's because I've drawn it incorrectly. No. But you should be able to see it's symmetrical. And if you study this a little bit longer, you might kind of notice that you see the same sort of pattern in each row, in each column, and that is when you're combining one of these 4 atomic types, the most complicated type kind of always wins, right? Or the type that can represent the most number of values always wins, right? There's 3 possible logical vectors, true, false, and NA. There's like, well, I can't remember exactly how many integers there are, but there are definitely more doubles, more real values than integers. And then, of course, there are even more character. A character vector can contain a string of any length, so that's the most complicated. So we can even simplify this even further, right? So if basically you take whenever you're combining 2 atomic vectors, you just put them together on this diagram, and the one you just follow the arrows until they meet up. When following the arrows is very easy here because it's just one line. And so I think even if you've never explicitly learned this before, you just by using R, you kind of pick this up. So that there's this theory here, and it's a pretty simple theory, right? Because I can show it on this diagram with just 3 arrows. So it's a pretty simple theory but you don't have to learn it because it's simple. Just by using R over time, you're going to internalize these ideas. And I think this is kind of, to me, one of the big benefits of theory. It's not that when you're starting out, you should learn this theory, but because there is this underlying structure, as you learn R, you'll kind of internalize some of that theory yourself, and it'll allow you to make accurate predictions about what a function is going to return. And so this is kind of my hope in the tools like ggplot2 and dplyr, that there is some like rich and, in my opinion, beautiful theory underlying that, but you're not forced to learn that theory right from the get-go. You can just experiment, and because there is this theory, you'll kind of learn it yourself. You'll discover it yourself, and then later on, if you want to go back, and you can formally study it. And I think that that's often helpful, but you're not forced to do that from day one. Now, the place where C starts to break down is when we start to move away from these atomic vectors. So the next level of complexity up are these S3 vectors. So these are called S3 because of complicated historical reasons. These are created using the third version of the object-oriented system from S, so S3. And these are not atoms, these are things that are built up from these atoms. Because when you look at these atoms, you notice there's a lot of really important data types that you cannot use. So for example, 3 really important data types, which I've shown you a little bit already, are factors, POSIX-CT. Again, POSIX-CT is just a really bad name for date times. POSIX is this, I don't even remember what POSIX stands for, but it's some like standard. And then the C here, C and T stands for calendar time. So whenever you see POSIX-CT, you just have to translate that in your head to a date time. This is something measured so a date is measured to the nearest day. A date time is measured to the nearest second or fraction of a second. And it has this unfortunate POSIX-CT name. So under the hood, if you peel back sort of R's lies about a factor to you, you discover a factor is actually an integer. And if you peel back a date or a date time, you find that under a hood it's actually a double vector, a vector of real numbers. So on top of these atomic vectors, we can use R's S3 class to build up these more complicated types of vector, which allow us to represent other types of data that we need. And so recently I've been spending a lot of time on this. There's a new package called Vectors, which has, I think, a pretty awesome logo. And the hope of the Vectors package, however, is that you will never have to know about it or learn about it, but it will provide this kind of theory that describes how should these different types of vectors work together. And so that when new people like me are developing new packages, that we can make sure that there's this underlying theory that you can learn, that you don't have to learn explicitly, that you just pick it up over time. And so that when you're when you're using functions, your naive predictions based on what you have learned, what you have seen in R already, are more likely to be correct. You don't have to learn some rich and complicated theory in order to make accurate predictions. Your experience alone should be enough. And I think this kind of gives us, this idea of types is a fairly good lens to kind of look at different packages in the tidyverse. So for example, the dplyr package, the key verbs in the dplyr package are all about data frames, right? Mutate, filter, select, arrange, and summarize. They all take a data frame as input. You give them some additional arguments in order to tell what to do, but they all start with a data frame, and they all return a data frame as well. So one way that I sometimes see people using dplyr incorrectly is they try and use dplyr when they've got individual vectors or individual columns. That's not what dplyr is about. dplyr is about working with, by and large, with a whole data frame. So I think thinking about these types, this kind of big picture, what's the type of this thing I'm working with, is a really kind of useful, high level way of framing what does a function do. And then the last function down here, which is a little bit more complicated, is the group by function. So the group by function in dplyr is a little bit weird because it doesn't really do anything. Right, when you tell dplyr to group your data, that function doesn't really do anything. It changes how all of the other functions behave. So all that group by does really is it takes a data frame and it returns this grouped data frame, which all of these other verbs know what to do with. Now, there are a few exceptions to this rule in dplyr. So most of the dplyr functions are to do with data frames. But dplyr also provides some functions that help you work with individual vectors. So how many of you have heard of the if-else function before? Okay, well, since you haven't, let's do a quick demo. So there's an if-else function in base R. Let's just create some random numbers. Here's 10 random numbers. And what if-else allows you to do is say, like, if x is greater than, or let's say less than 0.5, I want it to say heads, and otherwise I want it to say tails. So if-else is like a vectorized if statement. So it's going to say, for each of the elements in this vector, if it is true, say heads, if it is false, say tails. So if you've never heard of if-else before, and that is all you remember from this talk, hopefully you've still got your money's worth. So if-else, so there's if-else in base R, and then dplyr also provides this if_else function. And why does it do that? Well, if you look at the documentation for if-else, you can say, what does if-else return? And so if-else returns a vector the same length and attributes as this test vector. So that's this thing, which is a logical vector. And then through magic that I don't want to explain, sort of the C magic, because you've got a logical vector and you combine it with a character vector, you get a character vector. So that's what the result of this if-else function is. So if we kind of write it like types, like how do we describe what if you have like a logical vector here and a character vector here? If you read the documentation carefully, it feels like this should return a logical vector. So basically, if-else in base R has this sort of these weird semantics around type that are very confusing to me. And so instead, I created this if_else function in dplyr with the idea that it would have these, it would be easier to understand. I don't know if I've succeeded in that for reasons I'll show you shortly. But the idea is should be fairly straightforward, right? The first thing you give if-else is always a logical vector. Then you give it what it should return if that logical is true, and then you should give it if what that logical is false. So if the true value and the false value are the same type of thing, it's pretty obvious what it should return, right? So in this case, it's pretty obvious that this should return a character vector. And if I replace these with numbers, it's pretty obvious that that should return a vector of numbers. But what happens if you combine them? What should that return? Well, currently what it returns in dplyr is an error. And a lot of what I've been thinking about lately is that the right thing to do? Like, what should you do when you combine all these different types of vectors? And in particular, this leads to one really annoying thing with this function, is that you often want to do something like this. If the value, so here I'm saying if the value is greater than 0.5, just use the existing value. Otherwise, replace it with a missing value. And if you do that, currently, you get an error. And that is because this missing value is a logical missing value. And what you probably have no idea is that in R, there are actually 4 different missing values. There's NA, which is what you use all the time. There's NA underscore integer. There's NA underscore real, which is the missing value used for double vectors. You'll notice it's called real, again, for horrible historical reasons that you have no interest in learning. And then finally, you've got NA character. So what dplyr currently forces you to do is if you want to use dplyr as if else, you're kind of forced to learn about all of this. You're forced to learn about this theory about missing values, right? And I think, I think learning about the theory of missing values is kind of like fun and interesting, but I certainly don't believe that everyone believes that, and you certainly shouldn't be forced to learn that before you can use this useful function. So what I've been thinking a lot about is like, how can we make this more straightforward? And I think the principle here is that there should only be the one thing I am certain of is that there should only be one principle that you have to learn, not one principle for if else, not one principle for C, not one principle for another function. And so I think what you should get here is if you have different types here, it should ideally use the same rules as the C function. With one caveat, and that is the C function in base R, as I hopefully showed you earlier, is basically crazy. It is very, very difficult to predict what it is going to return when you start combining these more complicated things. So in this vectors function, we have this vec_c. In the vectors package, we have this vec_c function, which hopefully behaves like C, but is a little less crazy. So in this case, if you use if-else and you want to have integers and logicals mixed into the output, then we can just apply these usual rules, these simple rules for atomic vectors. And when we combine an integer and a logical together, we get an integer. What happens if you combine a factor and a character together? Well, currently that gives you an error. And whether or not that is the correct behavior, when I created this, I was like, yes, that you should be strict. If you try and mix a character with a factor vector, those are clearly 2 different things. If you complain, you should force the user to make that decision. That's like Hadley as the programmer. When Hadley as the practitioner sits down to do some data science, I'm like, it's a factor and a character. Just merge them together for me. So I don't know whether this is the correct behavior or not, but what I really do believe is that there should be one principle that is applied systematically everywhere rather than 5 different principles which get applied in different locations. So I'm not saying I don't know if this is the correct behavior, but there should be a correct behavior that gets used everywhere. Okay, so to kind of summarize these sort of 3 different parts of the talk, what I think about a lot as a programmer, as someone creates packages that are used by other people, is how do I make functions that give you useful error messages when you use them incorrectly? Because I am not there in front of the computer with you. I can't kind of interact directly with your code, with your data and say, oh, you've messed this up. Oh, you should have done that. Maybe work 3 steps back and do this a little bit differently. I need to think about how do I write code that gives you useful error messages, that gives you useful data that you can use to fix your data analysis or improve your data analysis. And one tool that has been really useful for me is thinking about the types of functions. What sort of thing does this function work with? Does it work with a data frame? Does it work with a vector? Does it work with an integer vector? Or does it work with a factor? And then particularly when you start working with functions that combine different types of vectors, most particularly the C function, what are the underlying set of principles that determine what type of thing you should get when you mix 2 types of input? I think that's more important. The more you the more you move along this continuum towards the programmer, the more important that is. But I think even when you're a practitioner, like thinking about just thinking very broadly, not about exactly what are the values this function is going to return, what exactly this function does, but what are the kind of the shapes of the input and the output, and how can you plug them together to solve a complex problem with small, simple functions, I think is important. So if you would like to refer to this talk, again, I have put it up on this link. The main things I think you should take away from this talk, if you want entertainment, I highly recommend watching the full video on these doors. These are called Norman doors in honor of Don Norman. Doors that look like you should pull them, but you have to push them. There are some Norman doors at the entrance of this hotel if you'd like to experience them in person. I'd also highly recommend this WHAT talk for Destroy All Software. If someone ever gives you, like mocks you for using R because they're like, R is like this crazy language that does insane things, watch this talk and then you'll be like, wow, JavaScript, which is like one of the most popular languages today, is like just as insane in R in different aspects. So if you ever need ammunition when people mock you for using R because they're silly, tell them you should watch this video. If you're interested in kind of the theoretical ideas that I've talked a little bit about today, I'm writing about them in this vectors package. If you're interested more in the application, like what are these hierarchy of types, this is still theoretical, it's less theoretical than this. But you can look at the vectors chapter in Advanced R, which I've been working on lately. Oops. I'll just quickly show you that if I was connected to the internet, which I'm not going to do easily, so I will not show you that. But so this is the link is to the second edition of Advanced R, which I'm working on at the moment. The goal of Advanced R, again, is to kind of help you move along this continuum from practitioner to programmer to kind of explain how it works, not as an environment for doing data science, but as a programming language. So if you want to understand a little bit more about the theory underlying R, and again, I don't think you should be forced to do this, but I think it is useful to understand more about the theory because it will help you write more correct code the first time. Take a look. This work in progress second edition has literally 1 million times more diagrams than the first edition. Lots and lots of pictures because I think pictures are a really useful way of kind of helping understand what's going on without diving into all the details. You can, of course, dive into the details if you want to, but hopefully the pictures give you kind of a good high-level overview of what's going on in R again. And I hope you appreciate it. It took me 15 minutes to create this recursive screenshot. So anything in all of the slides up at bit.ly/everydayfunctions. Thank you.
I'll be joined. Oh, brilliant. Hello, everybody. I'll be joining you on stage for this part. Before we begin, I would like to invite you to ask your questions via this link here. So it's dsc.network/Q/A/Tesla with a capital T. Please ask your questions via this link. And until you do, I have the first question for Hadley here. And considering that this is quite a riveting talk and covers a lot of topics, what led you on this path of, as a data scientist and now with creating these packages? Cliff Notes version, let's say.
So I think, when I think about what led me to this stuff, this is really, I still remember, when I was an undergraduate, I majored in computer science. And I still vividly remember the first time I started using R, I was like, this language is crazy. I have no idea how it works. And I think like a lot of like computer scientists and a lot of programmers like sort of stop there. They're like, this is weird and horrible. I'm going to use something else. But for some reason, it really intrigued me as a programming language. It is like legitimately different to most other programming languages in use today. And there are certainly some like weird quirks and like obvious mistakes in R, but there are also a lot of like really deep and brilliant ideas that make it a really, really good fit for data science. And that kind of like, it got me interested in that. And then ever since, I've just trying to be digging deeper and deeper and deeper, like, why does R work the way it does? Like, how can we make it better? How can we reinforce the good parts? How can we make the bad parts go away?
Well, I'm sure, as with many in these rooms, that was the case. Okay, so I have my first question here. What is your favorite package outside the Hadleyverse?
So I can barely bring myself to say the word Hadleyverse because it sounds so overweeningly arrogant. So I prefer the word tidyverse. Like, first of all, because it's not about me. There's a bunch of really great people working collaboratively on these packages. But what are the packages like? I don't know. So like, first of all, if I'm going to recommend packages, like, I just don't, like, since I don't do data science that much, I don't know if my recommendations are that great, but I really like, and a few that just come to mind, like the GG Repel package. Also, since I can't use the internet, like my brain is half disabled, so I'll try and do that. But how many of you heard of GG Repel? Okay, GG Repel, basically, like when you're trying to label a scatter plot that has 100 points on it and you label it and all the labels are on top of each other, GG Repel like automatically places the labels that they don't overlap, which I think is really, really neat. And I'm going to try, higher Wi-Fi, there we go.
Okay, perhaps we can move on to the next one because we have quite a few here.
Sure.
But yeah, see, Hadleyverse, shared universes are quite a thing these days, aren't they? So another question from Milos here. Isn't it easier to use Python rather than R?
If you already know Python, yes, I 100% agree that it's easier to use Python for data analysis than R. I do not, however, agree that that Python is like easier to use. One thing, and I'm probably gonna like, I saw one little example. I'm not very good at Python. I'm gonna try and recreate this from memory. Like computing a mean in Python, you do something like, just please excuse me if this is hereditary. You do like np dot, something like this to, whoops, you don't put semicolons at the end. That's something like how you create a computer mean in Python, hopefully, in the general ballpark. And I think this sort of whereas like in R, you do this. And I think this kind of shows a little bit of the difference of the heritage. Like Python is a programming language, and in programming languages, you want to be explicit about like all of the things you're importing into your current environment, and then you think Python is an object-oriented programming language, so you often think about methods of objects, whereas R is like, as well as being a programming language, it's also this interactive environment for statistics, so you kind of get like mean right out of the box. The other thing that like drives me insane in Python, and I've actually I filed an issue in the Jupyter notebooks about this, is that like whenever you have a floating point number in Python, it prints out all of the digits. And I'm just like that. I mean, R just prints out like 6 digits, which I think is too much. And I know some people really don't. And so like Tibbles now, some people really hate this, but I think this is a good idea. Tibbles only show you like 3 significant figures, because after 3 significant figures, like, doesn't really matter. Like, it doesn't matter because there are always more sources of variation in your analysis than, like, you're getting adding extra precision to your numbers is meaningless because there's way other more important things you should be worrying about.
Thank you for this. I'll have another one with on this, let's say, thing. Why not just use Java?
I don't even know it like that. Java. So one of the things, I'm not even going to try and write Java code, but I think I'm just going to show you like a little snippet of, like I think the thing that is so beautiful about R is the concision it gives you in expressing like, I want to take this empty cars data set, I want to group it by cylinder, and then I want to summarize it to compute the number of observations and the average miles per gallon. Like, this concision, you can read this as a sentence, right? Take empty cars, and then group it by cylinder, and then summarize it. This is the thing that makes R both like incredibly beautiful, I think, and moderately horrifying. This is the thing that makes R different to every other programming language, every other popular programming language today. The ease at which you can kind of abuse the language for good. And particularly here, right, when I say MPG here, the thing that's important about this MPG is it comes from this data set. We're using a different set of rules to look up values inside this expression. And that makes like R like kind of, on the spectrum of kind of like programming languages, it kind of makes R like very succinct for data analyses, which is really important because you've got that interactive conversation between you and the computer, and you want the computer to get out of your way as much as possible. You want to get the ideas in your head into the computer as quickly as possible, and that concision is really, really important, and because you're in that interactive context, you can tolerate some ambiguity. Other programming languages, or basically every programming language ever, requires you to be more verbose and more explicit, which is great when your code is being run outside of your control. Like, this is what makes Python, like, on average, a little bit more suited for production because you have to be more explicit, but at the same time, it makes data analysis, interactive data science a little less fluid because you don't have this ambiguity. There's less opportunities for a conversation between you and your computer. So I think this is like, to me, like, this is what makes R so great. The fact that you can create these domain-specific languages for visualization, for data analysis, that allow you to write so little code, so as little code as possible, and express like pure data science ideas as purely as possible.
Thank you. And I have one final question for you. Are there any other metrics, when talking about what makes a good function or a bad function, are there any other metrics that we can measure it by, like reusability or something like that?
Yes. Yes, there definitely are. Can I tell you what those metrics are? Maybe I can take a stab. So I kind of think about, like, when I think about like functions, I tend to think about kind of three things. Like, when you read the function, like, well, okay, so first of all, you want your function to be correct, right? It should do what it says it's going to do. If your mean function does not correctly compute the mean, nothing else matters. So correctness is like the first metric. But then when you think about the next metric, I think, is like, can you understand what the function is doing? Does it kind of elegantly express the intent of the function so that when you read it, you can understand it? And I think that's really important because if you can't understand what the function is doing, when you later on go to change it, because demands have changed, what you need that function to do have changed, if you cannot understand it, the chances of you correctly making the change are very, very small. And then kind of finally after that, I think, ideally you want a good function to be kind of performant, not in any like absolute sense, but it should be just like fast enough, so ideally that it's not the bottleneck in your analysis. So I think like when you look at the tidyverse as a whole, it is sometimes, but not often, the fastest in terms of computational performance, because I think that, like, while that's important, what I tend to spend more time thinking about is like, how can we optimize getting the ideas out of your brain and onto the computer? Because certainly, like in my experience, that tends to be the biggest bottleneck. So I spend a lot of time thinking about like expressiveness and how can you communicate through your code? How can you write code that like other people understand? Because one of those other people is going to be future you. Because in 6 months' time, if you are like me, you have absolutely no idea what you were thinking when you were writing a function. And so you have to kind of like reread your own code as if it has been written by a stranger, or certainly I do. And so being able to express your ideas like clearly is really, really important. So I think that, like, to me, that is what you should focus on. Like, you know, when you're starting out in data science, focus on expressing like your ideas as clearly as possible. You are not going to be able to do that off the bat. Just like when you write a report, when you communicate with other humans, like the first time you express your ideas, it's not going to be the best. You're going to have to write and rewrite and rewrite until you get to something that clearly communicates its intent. You don't always have the time to do that because you've got some deadline, you've got something you need to do today, but spending that time thinking about how can you rewrite things to be clearer, to communicate better, I think is really, really important.
Brilliant. Unfortunately, we ran out of time for questions. I still see some here, so I would like to invite you to talk to Hadley during the breaks. As of course, there are some very good questions here. Now, before we go to the break, I would like to thank Hadley here for his keynote talk. And on behalf of the conference, I would also like to give you this certificate of appreciation.
Thank you. Thank you.